Hi everyone, this is Jake Fry again, and today I'm going to talk about velocity. Okay, so remember that we have been talking about how to describe motion in its most basic ways and how to apply useful concepts in mathematics in order to make a problem easier to solve. And so in our previous lecture, we explained how to describe an object's position and its time. And so that included things like the displacement vector, a concept of scalar time, and then also intervals of both time and space. And we showed that it's very convenient to set up a problem using the center of mass in order to reduce a very complicated object that you're trying to describe into a single point that you can track that point's movement around. And also by applying a coordinate system onto the problem in order to make it easier for you to mathematically solve. And so in our daily lives, it's very uncommon for us to describe the motion of an object just by saying the position of the object at multiple different points in time. So instead, it is far more common to describe the average speed of an object. And so what do I mean by this? So for example, we can use baseball, which happens to be my favorite sport, so that's why it's an example. And so a pitcher stands at a distance 60 feet 6 inches from home plate when he throws the ball. And so we can apply a coordinate system onto this problem by saying, okay, right above home plate is at a radius equals 0, and then all the way where the pitcher is 60.5 feet. So at the beginning of the problem, at t1 equals 0 seconds, the pitcher just releases the ball at a radius, or r1, of 60.5 feet, and then the ball passes the plate at t2 is 0.41 seconds, or r2 equals 0 feet. And so by using displacement and also time intervals, that would mean that our delta r is 60.5 feet and our delta t is 0.41 seconds. And so it's far more natural just to say the average speed of the baseball as it travels from a pitcher's hand to home plate. Because if you were listening to a ball game and the announcer was saying, oh, the pitcher threw a fastball and it went 60.5 feet in 0.41 seconds, it would be even more boring than a lot of people think baseball is already. So instead, what they say is, okay, what's the average speed of the pitch that they just threw? And so in this example, it was 100 miles an hour, which would be quite a good fastball. Okay, and now for other types of everyday life occurrences. For example, if you're driving a car. So you need a way to measure your rate of change in your position without needing both a ruler and a stopwatch. And so the reason for this is because you'll see when you're driving along the road, speed limit signs. And you want to know if you're below that speed limit so that you don't, get pulled over by the cops. And so this is a, common dashboard, I guess, in a European country with kilometers per hour for the speedometer. But so it does have things like, the distance measured and also the time. So there's a clock for the time and there's the odometer showing how many miles your car has driven. So you could, if your speedometer is broken, do a very rough calculation while you're driving, of course, in order to see how fast you're going. But it's much more difficult to try to convince a police officer that you weren't speeding by using those measurements. Instead, everyone uses their speedometer because that directly gives you your average speed. And in fact, this would be more your instantaneous speed. And so you'll be pulled over by the police if your instantaneous speed is exceeding the speed limit and not your average speed, typically. Unless there's cameras taking your average speed over a distance. Okay, so how do we calculate this average speed? So the average speed is just your displacement, your distance traveled, divided by your time elapsed. And so when it's just the distance, so distance is actually a scalar quantity. And so when you have a scalar quantity divided by another scalar quantity, that means that you end up with a scalar quantity. And so that's why speed is a scalar. But if you were to use displacement, so distance as well as the direction, or delta r, then you would have a delta r, which is a vector, divided by a scalar, delta t, time elapsed. And so since it's a vector divided by a scalar, that gives you a vector again. So this delta r divided by delta t would give you the average velocity. And so one thing that's important to notice is that the direction of the velocity is the same as the displacement vector's direction. And this kind of makes sense because if you keep measuring your displacement delta r, if you're continually going north and you say north is the positive y direction if you're using Cartesian coordinates, it'd be weird to think that your average velocity, if nothing is changing and you just keep going north, it'd be weird if it was like, oh, even though I continually travel north, I'm going to have a negative average velocity, so negative y direction, or velocity towards the south. That wouldn't make any sense. So if you have a single vector on the right-hand side divided by a scalar, you end up with a vector that goes along the same direction as the original vector. Okay, so now for an example. So if we have two boats, one going north, this delta RA, and so you have 5 miles as the total distance, and the direction of that distance is north, which gives you both a distance and a direction, so that's a vector. And then you have another boat going 5 miles east, so 5 miles is the displacement, and east is the direction. And say your change in time is a quarter hour, 15 minutes. So then you can calculate, okay, what is our average speed over that time? So it'd be just 5 miles divided by 0.25 hours, which gives you 20 miles per hour. And so that 20 miles per hour is the same in both the boat that heads north and the boat that goes to the east. And that's because the average speed is not a vector, and it only cares about the distance traveled and the average time. But if you have the velocity, then it would also include the original direction that it was pointing. So for the boat A, I guess, it would be 20 miles per hour north, and boat B is 20 miles per hour east. All right, so now another very convenient thing that you can do is to use reference frames. And so reference frames are an individual coordinate system that's attached at a given time. So it's very common to have, at the origin of one reference frame at time t, say, a ball is at the origin, and this ball is moving in a direction. But I guess in this example that I have here, it's moving along the x direction. So at time t equals t, you use the coordinate system with x, y, and z. And then at t equals t prime, at some later time, you use a new coordinate system with prime variables. So it's t prime and x prime, y prime, z prime. And so this gives you the ability to translate a reference frame along with your object. And so while that's kind of a weird thing to think about, it's very convenient in a lot of times when you have two different objects moving. So we'll see. All right, so you can say that even if the object is moving within a stationary reference frame, you can always choose a new reference frame where your object is stationary. And so long as the velocity of the reference frame itself is constant, it's known as an inertial reference frame. And so we'll get back to this idea much later in relativity. But for what's called Galilean transformations, you can always transform a reference frame along with an object in order to describe the motion that's happening. And also, just like with any frame of reference, you don't need your Cartesian coordinate system, this rectilinear coordinates that I've shown here. You can use any type, spherical, curvilinear, whatever you want. And so I'm going to show lots of examples later where I use polar coordinates, since that's, probably more convenient coordinate system in physics than rectilinear. Okay, so why would we need this idea of reference frames and inertial reference frames? Because you can always describe an object just by a fixed reference frame and see what's its speed, what's its velocity or displacement, and its time. And so one very common thing is, you want a reference frame where you're the observer in order to see, what's going to happen in comparison with another object. So for example, if you have two cars that are described with velocities in the rest frame, we would typically understand the motion better if like one car would overtake the other if we look at the relative velocity between the two cars. So for example, if the lead car is going an average speed of 60 miles per hour and the car behind is going 65 miles per hour, both in a rest frame, so like at the start line of the track, then we would know that if there's enough track left, that eventually the car that's going faster will overtake. But what we could also do is we could assign the following car to be the car at rest. So basically, say you're the driver in the following car. So from what you see, you're not going to say that the lead car is going 65 miles per hour without making, a conscious effort to be like, okay, I'm going, 65 miles an hour and the other one's going 60 miles an hour. Anyway, you would basically be like, oh, it looks like that car is coming closer to me, or it has a negative net velocity. So if you had a frame of rest as you driving the car behind, then you would say that the car in front is traveling at -5 miles per hour. And so it would appear that the first car is actually slowing down. And so this is a mathematical trick that can be useful in many problems describing the motion between two objects, such as racing cars. And then also, describing relative motion is very useful when you have, a person inside of another moving object. So basically, if you're inside of a plane and the plane is traveling, like 300 miles an hour, and you walk to go to the bathroom, you're not going to say, oh, I was walking at 300 miles per hour plus, 1 mile per hour, however fast you're walking. You wouldn't be like, I'm 301 miles an hour. You would say that you're, walking at 1 mile an hour. And so that's using a rest frame of you inside of a frame of reference that's actually moving at 300 miles an hour. And so, or I guess I chose 3 miles an hour instead of 1. So it depends how fast you are walking if you need to use the bathroom. So these frames of reference allow us to both more easily mathematically describe two objects as they're moving along one another. And it allows us to describe a mathematical problem in a more natural feeling way. So by attaching yourself onto a rest frame and seeing how the objects move around you. And so, at this point, it's not super helpful or useful to use one type of system to describe the motion versus another. But we'll see when I get to some examples later on when you would decide for simple mathematical problems if you're going to use this inertial reference frame idea to do a Galilean transformation, or if you'll just have a fixed frame of reference for all the moving objects around. And so hopefully you'll come back for our next lecture to describe, the next step, which is the rate of change of the positions rate of change, so acceleration.